Kimsenin sorusu yok herhalde. Okey, sorunuz yoksa bir sonraki konuya geçeceğim. Okay, no questions. So I will continue with the next algorithm that we are going to cover, which is merge sort. Probably you all know what merge sort is. We are going to go over the algorithm and try to talk about a little more on analysis, the performance of the merge sort. So before going over the merge sort operation, first we are going to talk about the basic operation in merge sort, which is a merge operation. Merge is a well-known process of merging two sequences. Of course, this two sequences has to be ordered. So we are merging ordered sequences. Both sequences are ordered based on the same comparison technique. So the elements are compared based on the same criterion. Okay, a common comparative method is used for both sequences. So in this case, we can put these two sequences together into, combine them into one unique sequence, okay? So the result of merge operation is a third sequence containing all the data from the two sequences. Okay, we all know what merge operation is probably. In merge operation, for example, this is sequence 1, this is sequence 2. The size of these sequences doesn't need to be same, but in merge sort, these sizes will be very similar, even if not same. For example, here the first sequence has 3 elements and second sequence is 4 elements. As you see, they are both sorted, and we try to put them together into an output sequence, single output sequence. Again, the output sequence is sorted from smallest to largest, right? How we are going to do it? First, we access the first elements in both sequences, okay? And compare these two elements and copy the smallest one into the first position in the output sequence and continue with the next element in the sequence that the smallest coming from. And we continue this process until one of the sequences is exhausted. So first we get the first elements from both sequences and continue while the both sequences are not finished or neither of them are exhausted. And what we do is compare the current items. For example, right now the current item is 311 and 324, right? We compare them and pick the smaller one, copy the smaller current item to output sequence. So 311 is copied here. And from that sequence, that's smaller coming from, the next item from the input sequence whose item was copied is selected. So we select 478 and continue like that. We compare 478 and 324. 324 is smaller. We copy it and continue with the next item over there. We compare 478, 15. 415 is smaller. We copy it. Continue with 499. Then we compare 478 and 499. 478 is smaller, so we copy it over here. And the first subsequence is exhausted. So we get out of the while loop. And when we get out of the while loop, one of the array is completely processed, but in the other, we still have some elements. And we copy these elements into output sequence one by one. Right? If there are remaining items in the first sequence, we copy to the output sequence and do the same for the second sequence as well. One of these two steps, step 4 and step 5, will copy nothing, right? Since one of the sequences completely processed. There's nothing left in one of the sequences, right? So this is the algorithm for merge operation. As you see, it's a simple algorithm, and it performs, it goes through both sequences one by one. And after each comparison, a value is copied. For example, after comparing these two values, we put a value in output sequence. After comparing these two values, we put an element, right? After comparing these two values, we put one element. After comparing, we put one element. After comparing, we put one element, right? And the rest is copied later on, one by one again. So the number of comparison here is not more than total size of these two sequences, right? If both sequences contain n elements, each element needs to be moved from input sequence to output sequence. So each element in both these sequences has to be moved into here. And each move operation is after a comparison, or if there are remaining elements after all move operations are completed. That's why merge takes linear time. So this operation takes linear time to the total number of elements here, or with the size of the output sequence. And here, if there are n elements in each sequence, we will have 2n values in output sequence, and running time will be theta 2n, and it is same as theta n, right? So the running time is theta n. But this is runtime performance. What about space requirement? We have these two input sequences. We cannot merge these two sequences in their place. So without using an extra output array, we cannot merge it. There is no simple way of doing it. Of course, there are some advanced algorithms to perform that, but we are not going to talk about them. But for the time being, we can assume that there's no way to merge these two arrays into one without using extra space for the output array. So this output array is of size theta n to n over n. So we have an additional space requirement of linear space in this merge operation. So this is important. Merge operation takes linear time and requires linear extra space. Okay, we are going to use it. And this is the code for merge operation. Merge takes two sequences, which both are ordered sequences, and put these sequences into this output sequence by merging them in sorted order. As you see, we keep three indices. I is for the left sequence, J is for the right input sequence, and K is for the output sequence. All initialized to be 0. So our current element is the first one for both input sequences. And while I is less than the length of the right sequence and J is less than right sequence, which means while there are more elements in both sequences, we compare the elements, current elements, and based on the result of this comparison, one of the elements will be copied into the output sequence. And the copied place is incremented as well as the output sequence, as you see. In time, both I and J may increment, and one of them will exceed the length of the subarray, sequence, input sequence. So one of the sequences, input sequences, will be exhausted. Then we copy the rest for both sequences. As I said, one of the sequences has more items to copy and the other one has no. So the order of these two part is not important since one of them will perform copying. Okay. So this is the code. In merge sort, we do not perform merge operation right away since we don't have any sorted sequence. But we put the array into true halves and sort both halves somehow, sorted sequences. Then we merge them together into one sorted sequence. So this operation is merge operation. But how we are gonna make this subarrays to be sorted? We are gonna perform this sort operation recursively. So this algorithm is a good example of divide and conquer. This is an algorithm design technique that you are going to cover in more detail in course 221, CSE221, Design and Analysis of Algorithms course. right? But in this algorithm, first we split the array into two halves, sort the first half recursively, sort the right half recursively, and merge these sorted two halves together to get the sorted sequence of the original array. Okay, so the algorithm is simple. This is the same algorithm, but in a little bit more detail. Half size is the table size divided by 2, or the elements, the half of the way into the array. The left table will be of half size. Right table will be the size that can hold the rest of the array. And we copy the first half into left table and the second half the right table. So after this sixth step, we have two left and right tables. We sort left table recursively by applying the merge sort. Similarly, we sort right table recursively applying the merge sort algorithm again. So after this two operations, 7 and 8, we have two sorted sequences. Right now, these are sorted from smallest to largest. We merge them together into original array. Apply the merge operation, merge left table and right table on the original table, which is an output table as well. So we get an input table, sort them, and return it on the same table. But in the meantime, we use two tables, left table and right table, as an intermediate tables. And this is a recursive code. This recursion has to be stopped, terminated, and we terminate the recursion when the table size is equal to 1. If we have one element or less, we stop the recursion. Since one element table is already sorted, right? If there is 17 here, just one element, this sequence is sorted, right? Whatever the value, it is sorted. So we stop the recursion when we have one element or no element. Both are sorted. If we have more than one element, we divide that table into two halves, sort them, and merge them. Okay, so there are three steps in the three basic steps in divide and conquer. We divide. This part is divide, dividing the original array into two subarray, or the original problem is divided into two subproblems of sorting left subarray and right subarray. Both subproblems are smaller in size than the original problem, but the problem is same, sorting a table, right? Since the problem is same, we can sort left table and right table recursively using the same algorithm. Since the algorithm solves the problem of sorting, and we have the problem of sorting as a sub-problem, as two sub-problems actually. We solve them one by one. So this step is recursive calls. At the end, we have a combine step. This is divide, recursion, and combine step. At the combine step, the result of two recursive calls are combined together, merged together, to get the solution of the original problem, the sorted sequence for the original whole array. Okay. Of course, in this divide and conquer technique, we use recursion, so there should be a base case for the recursion that stops the recursion, and this case is having 1 or 0 elements, and if that is the case, we do not need to do anything since the table is already sorted. Okay, let's talk about the trace of the merge sort. This is our sequence of 8 elements. First, we divide this elements into 2 subsequences. We form these 2 subsequences. And as you see here, after forming 2 subsequences, we recursively call for left subarray first. After we finish with the left subarray, we make a call for the right subarray, right? So after division, first we make a call for the left subarray. And since the number of elements in the left subarray is greater than 1, we are gonna perform a division again. And we continue with the left subarray. Since it is greater than 1 elements, we have to divide again. We call for the left subarray. So there is a call for the original problem, recursive call for this one, a recursive call for this one, right? Right now, there is no more recursive calls in the function stack, right? So in this recursive call, the number of elements is 1, right? So it returns right away. And of course, this returns right away. And we make a recursive call for 60. Since it has only 1 element, it returns right away. So in this recursive call, right now, 2 sorted sequences, and we have to merge them. And while merging them, we are going to use the same array, original array. First, we take the smallest one and copy, then largest one, so 50 and 60, as in here. So first 50 is copied and 60. So this is now sorted array. Remember, the sorting is completed. There was a recursive call here. There was a recursive call here. This makes the recursion call. This makes the recursive call for the last subarray, and this will return, right? Since it is sorted right now. After it returns, we make a recursive call for the right subarray, and when we call the right subarray, the number of elements is greater than 1, so we subdivide into the two sequences. And right now, there is a recursive call, recursive call, recursive call. It makes a recursive call for the last subarray. It returns right array since the number of elements is 1 and it's sorted. So it makes a recursive call for the right subarray. It will return right array. And now we have to merge these two elements. Of course, smaller one will be copied here. The larger one will be copied here, right? So this is the operation. So we have a recursive call, recursive call, recursive call, and this is sorted now. It will return as well. So for this recursive call, we make a recursive call for left subarray, and it's completed. We made a recursive call for right subarray, it's completed. Now we have to merge them together into original array. Of course, while merging, first we compare this true value and copy smaller one, and compare 45 with 50 and copy 45. And these two elements will be copied as a remaining element, right? So right now we have a recursive call here. We made a recursive call for the left subarray, and it is sorted, and it will be returned. After that, we make a recursive call for the left subarray. There is no recursive call here anymore. It is already returned. And then we will make two subarrays and make recursive calls, right? And since number of elements is greater than 1, we make two subarrays. And these are only one elements. The calls will be returned right away. And when we merge them together, 20 and 90 will be, this is sorted right now. So we made a recursive call for left subarray here. There is a recursive call here, recursive call here. This makes this recursive call, and it's returned. It will make a recursive call for the right subarray. It will divide the elements into two, and they will return right away. And when we merge them, this will be 15 and 80, and it will return, right? As in here. Right now, this recursive call made two recursive calls, and both of them are returned. So we have this sort subarray, this sorted subarray. We have to merge them, and this is after the merge operation. Okay, and this recursive call will return. Now we have this recursive call and two made two recursive calls, and both of them are finished. We have two sorted sequences. Then we have to merge them together to get the original array sorted. Okay. So this is the trace of the algorithm. So in a sense, we have some divide operations performed and combine operations performed, right? Again, these are divide operations, these are combine operations. So here we have something like this. It is like a tree, right? Then we combine them together, right? When we combine into larger and larger arrays. When we divide into smaller and smaller arrays, and when we combine in into larger and larger arrays. But number of steps here and number of steps here, number of divide stages and number of combine stages is logarithmic, right? Why? Because we divide each time to half. This is half size. This is half size. This is half size. And we stop, then we reach to 1, right? So logarithmic number of steps, divide steps are performed. Logarithmic number of combined steps are performed. Okay? At each step of divide, we here n elements are copied into 2 subsequences, right? So in the first stage, we copied n elements. In the second stage, there are n over 2 elements are copied into these n over 4 elements. This is n over 2, this is n over 4, this is n over 4. These are n over 4 as well, right? So n over 2 copies are performed here, n over 2 copies are performed here. Again, here as well, there are n elements copied. Here, n elements are copied. And here, again, n over 4, n over 4, n over 4, 4 times n over 4, n elements are copied. And it stays like that for all layers, all steps. And we have logarithmic number of steps, right? Similarly, in combined stage, we have 1 element here. We put them together to form 2 elements. But number of such things is n over 2. So n over 2 such combined operations of 2 elements happens. So while going over from 1 element to 2 elements, we perform 2 operations and n over 2 of them. While going from 2 to 4, we perform 4 operations and n over 4 of them. So each time again, we perform n operations for each combined stage. And how many of them? Log n of them, right? So for divide and combine stages, the total effort is n log n. So backward step means combined step requires moving of n elements from smaller size arrays, starting from 1 element arrays, to larger arrays, and it requires linear time at each level. And number of steps of number of layers, number of levels will be logarithmic because we make it half and half and half until 1 element. So the total effort will be theta n log n. And this theta n log n doesn't depend on the elements. Whatever the elements in the array are, whatever the values of the elements in the array, we always perform this match operation. So the running time is always n log n, theta n log n. There is no, for best case, it is theta n log n, and worst case is theta n log n. So the running time itself is theta n log n. Okay? So this is the table sizes. We start with table size of n, then we go to n over 2, then n over 4, n over 8, n over 16, etc. in this sequence. While going down through the recursive chain, the table sizes, right table and left table size are same, and the size will be decremented like this. So we will have and we will need these two tables extra for this level. We will need these 4 tables extra in this level, etc. But as you remember, we do not make this recursive, we make this recursive call, but this recursive call is not made, so these tables are not created. Actually, only a path from root to leaf leaves. So we will have n over 2 size array here, n over 4 size array here, go to until 1. That's why we have this many extra storage required, and this adds up to n minus 1, which is close to n. So theta n extra storage is required for this operation. Okay, so the running time is n log n, but linear extra storage is used. Remember, in merge, shell sort, insertion sort, or selection sort, the extra storage we used were constant. We have used 1 or 2 extra positions, extra elements positions only, but here linear extra space is required. It's a lot. This is the algorithm, and actually is the code for the sort operation, and we have the this base case. If the table length is less than or equal to 1, we do nothing. If it is greater than 1, we calculate the half size and create tables for right table and left table. Copy the elements in the table into right table and left table. Sort them, sort left table and right table recursively, and at the end we merge them together by merge operation. And we have already talked about the merge operation before, so the algorithm is completed. Any questions so far? Any question about the merge sort? Okay, this is the merge sort. As you see, we have linear extra space and n log n. When you compare quadratic running time sorting methods like insertion sorting, which is theta n squared in the worst case, right? For insertion sort, when you compare this true running time, n log n is a lot better than n squared. So you should prefer merge sort over insertion sort for large arrays. But remember, the insertion sort is linear time if the array is almost sorted. And you can prefer insertion sort if the array is almost sorted, since the merge sort will perform in n log n running time, even if the array is sorted or almost sorted. So for sorted or almost sorted arrays, insertion sort performs better, but for random arrays or very disturbed arrays, it's better to use merge sort since it performs better, which is n log n. We have another sorting operation, which is n log n, heap sort. As you see from the name, heap, it uses the heap data structure to sort the array. Remember the heap structure? Heap structure keeps the smallest element at the top, and the children of the for each node, the children are larger than the parent, right? So we can find the smallest element at the root. And if we put all the elements into heap, then we can keep an extra array, take out the smallest element and put here, and when we take out the smallest element, the heap will rearrange. Again, the smallest element will be at the top. We take out and put here, and continue like this until the heap is empty. Okay. This is a simple way of doing it. First, we have an input array. We construct a heap. And after that, we delete min until heap is empty, one by one, and move it onto the same array. Probably we can use the same array since it's, the elements are moved into the heap anyway, right? So to construct the heap, we can insert the elements one by one. Insert elements in array one by one into heap, right? So n elements should be inserted into a heap, and you should remember that insertion takes logarithmic time. So this operation takes n log n time. Actually, not theta, big O, since the insertion takes logarithmic time, but all log n time. And also delete operation takes all log n time. So n deletions has to be performed. This is all n log n as well. So the overall running time of heap sort is O n log n, is in a merge sort. Again, we have input array this is input array reused, right? But we use an extra heap. And the size of the heap is linear. So linear space is used in this method, as in merge sort. But we can get rid of this extra space easily by using array representation of the heap. We are going to talk about in a minute. So merge sort is n log n, still uses n extra storage. Heap sort will match the same running time or n log n time, but we are not going to use any additional storage. And heap sort, we will use heap to store the elements in the array. But we are not going to use extra array, since there is no additional storage used in this algorithm. How we are going to do it? This is the original array, right? The first element is heap. One element is always heap. And we will insert the next element into this heap. Inserting, then next element, then next element, then next element. It is like insertion sort, but this time we insert like heap, not to get a sorted sequence. Remember heap insertion? You check with the parent, and if it is smaller, we exchange, right? So after inserting all the elements here, this array itself will be a heap. So we didn't use any extra space for the heap right now. And after we get this heap, what we do is we have to delete the first element, right? How we delete the first element? We put that element aside and copy the last element in its place and make heapify operation, compare with the children and swap if it is necessary, right? But after delete operation, this last element is empty. So we can put this element in its position. Again, do the same thing. This is the smallest. Delete it. And this element will be moved here. This is not in the heap right now, right? So it is not touched. And heapify is performed. After heapify, this element is deleted anyway. It's empty. So we move in its position. So by this way, we can perform and delete operations. And at the end, the whole array is sorted, but largest to smallest, right? As I said, in heap, the smallest element at the top, and we move that element at the bottom, right? So the smallest element is at the end. But we can keep the heap during heap forming a heap. We can be smart and put the largest element here, not the smallest. So for regular structure, so each element is smaller than its parent and larger than its children. This is called max heap. We can build a max heap, and when we move the maximum element at the end and keep doing that, the result will be smallest to largest as we want, right, as we expected. So the algorithm is simple. This is the first version. So it will use an extra array. We use a priority queue, maintains the smallest value at the top. And we place the elements in the array into heap, which will take O n log n time, and remove each element one by one and put them back into the array, which takes another O n log n time. But this version requires extra storage for the heap, right? Here we have the algorithm. Insert each element one by one into heap, priority queue, then remove one by one and put them into the array from smallest to largest, right? From left to right into the array. But we use an additional storage for the heap. We can we do not need to use extra space for the heap. We can reuse the array, input array actually. And in the revised version, we also make that the parent is larger than the children. So each parent node is not less than its children, larger than children. So it becomes max heap. Move the top item to the bottom of the heap. Actually, a top item is moved at the bottom. So in that, by using that, we can get rid of the extra storage. So what happens is, this is the max heap. You can assume it like array 89, 76, 74, etc., like 29 and 6, right? First, we have to delete this value. Actually, we swap with the last element, and this is not part of the heap anymore. And we continue heapifying. We compare with the two children and pick this larger children and swap with it. Pick the larger children and swap with it, and continue like that. And this one is max heap. It becomes max heap again. 89 is not a part of the heap, but when you look at the array, 89 is at the end of the array here, and that's not part of the array, part of the heap. And we continue like that. Delete this 76 and put in the place of 29. Now these are not part of the heap, and we heapify, check whether largest child is larger or not. Largest child is 74 and it's larger, so we swap. Largest child is 66 and larger than 29, we swap. There is no child, so we stopped over there. Again, everything here is marked zip now. We continue with deleting next element and delete 74 and put in the place of 28. 28 is at the top, but this is not a heap anymore. Since the largest child, 66, is larger than 28, we have to swap. Largest child, 39, is greater than 28, we swap again. And we stop there since these elements are not in the heap, so there is no child actually here or here. There is no children of 28, so we stop over there. And this is max heap right now. And when you look at the array implementation, last three elements are 74, 76, and 89, and sorted, right? We put another element here, which is the largest, 66, in the next step by swapping this through. And now this is not heap. We get the largest child and swap. And for this one, largest child is 29, so we swap that since 29 is larger. And there's no child for 18, we step over there. These are not in the heap, but the rest is a heap, and we continue like that. Swap 6 with 39, 6 percolates down, as you see. And here we stop since this part is not part of heap. Actually, there is no child for 6 actually, right? And we continue. 37 is moved in place of 20, and 20 percolates down and down and stop there since these are not part of the heap. When you continue like this, as you see at the end, we will have this heap, only one element. All these are not part of the heap, and we can stop over there. Either we can delete it and put it in its place, it's also possible. And when you look at the array implementation of this thing, the first element is 6, then 18, then 20, 26, 28, etc. until 66, 74, 76, and 89, right? It is a sorted order in this level by level representation of this structure. So actually we do not keep a tree like this. Actually we keep an array of this sort. This is a original heap, and at the end the array becomes like this, and it is sorted. So each element removed will be placed at the end of the array, and heap is max heap, right? So the heap part of the array is decreased one by one. So this is not in the array, this is not in the heap, etc. After third delete, 3 elements at the end will not be part of the heap, etc. At the end, none of the array elements is part of the heap, and it is sorted from smallest to largest. So The algorithm is simple. Build a heap arranging elements in an unsorted array by inserting the elements from second element to nth element one by one, insert into heap. And the second, after building the heap, we delete the elements one by one. Of course, the largest element until the heap is empty. Remove the first item, which is the largest, and swap it with the last item. And of course, you should restore the heap property after deletion. And perform this operation again and again, delete elements one by one, and put at the end. Then what you get is the sorted sequence. So we consider first item to be heap, and so by building the heap, build the heap operation, this first item is heap. We insert this one, then this one, then this one by one, from first element, this is the 0th element, first element to n minus first element, right? And at the end, the whole array will be heap. This is the how this first rearrangement is performed. And starts with 1, and while it's less than table length, we insert nth element and increment n by 1, right? Of course, after each insert operation, we have to restore the heap property, right? So we have this part to be heap. We add this one as well, but we have to heapify with its parent, with its parent, with its parent, right? We swap with its parent, and if it is necessary, and it takes logarithmic time. So each insert is logarithmic time, each delete is logarithmic time. So building heap takes n log n, and removing all of them one by one takes n log n time. So the overall running time will be O n log n, and no extra storage is needed in heap sort. This is the code for heap sort. I'm not going to go into details since it is very similar to heap operation. You can check it out and try to understand. This is like insertion of the heap, insertion operation of the heap, and this is like deletion operation of the heap. You can check it out and try to understand it. Okay, I will stop here. Quick sort is the what is left. We have talked about shell sort, merge sort, and heap sort today. Tomorrow we are going to talk about quick sort and finish up this chapter. Okay, this is it for today. If you have a question, you can ask right now or tomorrow.
Have a nice day, sir.
Thank you.